Welcome to class meeting 29 of the Introduction to Optimization. There are two announcements. First, homework 6 is due on next Monday. There are 6 additional proof problems I assigned last time. Homework number 7 will be assigned soon. And you may say that it's too much, but anyway, we have to do that. As you know, we are going to cover the rest of the chapters very quickly, but you should be able to solve the problems in the exercises. Anyway, so let me give you a big picture of our 4th edition, the textbook. It has a little bit different arrangement of the materials. So it is part of the part 4 of our textbook. And part 4 is all about constraint optimizations, but especially with functional constraints. I never said this one, functional constraints. But this means that we have equality constraint function and inequality constraint function. Got it? So functional constraints means that we have a constraint set that can be described in this way. As I told you, an arbitrary constraint set may not be described in this way. So we are kind of consider a small subset of problems in the set of all constraint optimization problems. Here in chapter 20 of 4th edition, before it was chapter 19, we studied constraint optimizations with equality constraint function. So we have constraint like this. In chapter 21, we both have the inequality constraint function and equality constraint function. And you may say that, wait a minute, this is a special case of a general constraint optimization problems with equalities and inequalities. You are right, but the reason why we study this first is that actually in this case, what we are going to derive is almost the same as what we derive in chapter 20 with an equality, vector valued equality constraint function. So this is what I wrote last time, the page 7 of the handwriting. So here let me a little bit change because something is not correct. So here we will think about M equality, scalar valued equality constraint functions. So let me change this to M. Other than that, I believe it's okay. So this is the big picture we are going to study today and probably next class meeting. And here in chapter 20, we solve this kind of problem. So we have an objective function f0 and a vector valued equality constraint function. And there is no convexity assumption, no strong duality assumption. This could be non-convex problem. This may have a dual problem that does not satisfy strong duality. But we derive some interesting theorems, especially 3 interesting theorems. Probably today I will focus on this one most of the times, and we'll quickly generalize to this one because they two are almost the same. So here the first theorem looks like this. Suppose that x star, that is of course feasible, which means that satisfies this equality constraint, is a local extremizer, which means that it could be a minimizer or a maximizer, or actually none of that. But anyway, the derivative, how to say that? Not derivative, but anyway, around the feasible set, so at the neighborhood, there is no change. Virtually no change in the objective function value. And here goes some constraint. Because without this, we may not end up this conclusion. So we put some constraint called regularity. And this regularity is a little bit different from here and here. But basically they are the same. It looks different, but basically they are the same. The theorem has the conclusion like this. Given a local extremizer that is regular, we can find some vector nu star that has the same length as the length of this equality constraint function. And this constant exists such that what? The derivatives of component equality function, h sub j, okay, j from 1 to m, then you can find these gradients at x star. And interestingly, you can show that the gradient of your objective function value at this x star is a linear combination, as you see here, linear combination of the gradient vectors of the component equality constraint functions. And here, the combining coefficient vector is this nu. Got it? So it looks very similar to our first order, the first order derivative of our Lagrangian. As you remember, given this problem, the Lagrangian is a function of x and nu for the Lagrange multiplier for the equality constraint function. And you sum up the objective function and nu transpose h underscore, right? So this was your Lagrangian. And as you see here, this is nothing but the first order derivative of Lagrangian with respect to x. So here, as you see, in chapters 20 and 21, we always assume that these functions, objective and equality and inequality constraint functions are all continuously differentiable. Got it? So we have one more condition here. So let me write here. Here, for the first order necessary condition type results, we need these functions are continuously differentiable. And for these four second order conditions, we need second order continuous differentiability of these functions. So this involves the Hessian matrix of the objective function and Hessian matrix of each component inequality and equality constraint functions. Got it? So this is also different. So I missed that part last time. Okay. Let me remove this. Okay, got it? And for this constraint optimization problem with inequality and equality constraint functions, the theorem looks almost the same. The x star is a local extremizer, could be minimizer, could be a maximizer, and regular. Then there exists lambda star and nu star. The length of lambda star is the same as length of this inequality constraint function. And same for as before for nu. And as we have conventionally, this lambda associated with the inequality constraint function is said to be all non-negative, has all non-negative components. As you remember, when we defined the Lagrangian for this optimization problem, we wanted to find, in this minimization problem, we wanted to find a lower bound, right? As you remember. So this must be negative when x is feasible. As you see, if x is feasible, this part is anyway gone. But here, each component function is negative or 0. So we'd better have lambda I positive or 0. So we have this condition, as you remember. And then, similar to this first order necessary condition, we have the Lagrangian differentiated with respect to x, evaluated at x star is 0. What does that mean? Our objective function has gradient that is proportional to what? To this gradient of component equality functions and the gradient of component inequality constraint functions. So this is a linear combination of them. Got it? So they look almost the same. And related to what? Related to the differentiation of the Lagrangian. You remember that when we formulate a dual problem, we had what? We first formulated the Lagrangian. Okay, and we infimized Lagrangian over x only, okay, by choosing, for example, domain of these functions as a domain of the constraint set of this infimization. And we could show what? We could show that we could show that this value for any lambda and nu, for lambda positive, non-negative, okay, we can find a lower bound. Why this is so? First, consider x in omega. Then what happens? They are the same, right? Or, depending on this value, we may achieve what? A smaller value. So anyway, even with omega, we have this inequality. Now we increase the search space. Then this infimization may have more smaller value. Got it? Then we define this one as g of lambda nu, as you remember. And for all lambda nu satisfying this condition, this serves as a lower bound of our optimal function value. So we defined d star as max of g lambda nu over lambda and nu subject to lambda greater than or equal to 0, right? So what did you have? You had the weak duality, got it? But sometimes we satisfy the equality, So we have strong duality sometimes. And for this infimization, what can you do for this infimization? If these functions are all differentiable, then you may differentiate this function, right? As you learned in calculus, you may differentiate this function in this set. Okay? And then you may find this equals 0. You may find x satisfies derivative of this equals 0. Okay? That's what we did actually, as you remember. When this D has very nice property, right? If this D domain is very weird, then differentiation may not make sense. But in many cases, we find that this D or some other omega prime, I said, which is, for example, open, which is an open set. For example, some open interval, then you can differentiate at anywhere, right? So in that case, it's very nice to have such first or necessary condition type thing. Anyway, this is what we had, but we do not assume strong duality. If you remember, if strong duality holds, we can say a lot. What would we say if strong duality holds and the functions are differentiable? You remember if this holds, what can you say? They satisfy so-called KKT conditions, right? You remember. So what was that? First, X star satisfies the primal feasibility. So H of X star equals 0 and F of X star is less than or equal to 0. Second, dual feasibility. So what? Lambda star is greater than or equal to 0. What was the third condition of the KKT conditions? Complementary slackness. So you have transpose Fx star equals 0. And what is the fourth condition? That fourth condition is related to what? Differentiation of this one in the minimization, right? So we have gradient f of x star plus summation. Let me write it in a little bit different way. So d of f underscore x star and lambda star. I believe I'm right? Yeah. No. Okay. This is not correct. I'd better put transpose here. Okay. Then we have the gradient transposed, and each one has gradients here. So it's a linear combination. So this one and that one has the same number of columns, and they are row vectors. And we have d of h x star mu star equals 0. Got it? Yeah, I believe I'm correct. Okay. So compare which one? What I want to say is this one. Compare this one with that one. You see, they are the same actually. Got it? So you may say that if X is a local extremizer and regular, then lambda star nu star exists, and lambda star is dual feasible, you may say, and it satisfies what? It satisfies the fourth condition of the KKT conditions. Interestingly, here last time I did not wrote, but actually you have, if I remember correctly, you have complementary slackness type thing. Okay? If I remember correctly. Let me check. This is so confusing, so I'd better check. Yeah, I'm right. So this additional condition, the complementary slackness, must be there. So lambda star nu star exists, and lambda star is dual feasible, and it satisfies the complementary slackness, and it satisfies the fourth condition, the FONC type thing. Anyway, so you have the big picture. Got it? Almost the same thing appears again and again. But there is a huge difference. I emphasized last time. Here we have what? We have this given. Okay? Strong duality and optimality of x star and lambda star nu star. Primal optimal and dual optimal. And differentiability. Then this condition holds. So, for example, given an arbitrary optimization problem with equality and inequality constraint functions. For example, you have no idea about this, but you find some triplet x star, lambda star, nu star satisfying this condition. Then what can you say? What can you say? Can you say that they are primal and dual optimal? No. You may not say that. Okay? Do they result in strong duality? No, not necessarily. Okay? So be careful. Here, what you are going to study, actually you will use this theorem a lot. Okay? You will use this theorem a lot in studying the information theory and reading some communications research. Probably almost every papers related to optimizations. System optimization, parameter optimization, sequence optimization, even some optimal control. Okay? You will see some variation of this. Anyway, so the difference is that here there is no assumption. Okay? I take time because this is so important difference. There is no comment on strong duality. Okay? There is no comment on strong duality. There is no comment on dual optimality. Okay? Anyway, we are not deriving the Lagrangian dual function. Got it? We do not derive Lagrangian dual function. Of course, if you can derive the Lagrangian dual function, then actually by using these results, you may rely on this one. For example, you evaluate your f0 at x0. And you evaluate your g, the Lagrangian dual function, at lambda star nu star you have just found here, for example. And suppose their values are the same. Then what happens? You have strong duality. Right? And automatically your x star and lambda star nu star are primal and dual optimal. In that case, right? In that case, you have found the optimal solution. Global optimal solution. Okay? I never said local optimal. Okay? Global optimal solution. But here, this is different. They are all talking about local properties. Got it? So this is the difference. So suppose you are given some optimization problem like this, and you find x star, lambda star, u star satisfying this condition. What can you claim? Due to this regularity, you must be careful. Okay? For example, every feasible x is regular. You may be able to show that. And also, you have found every triplet satisfying this condition. Every triplet x star, lambda star, and u star satisfying this one. Then you are always guaranteed that you have found all candidate local extremizers. Am I right? Got it? Suppose x in omega, the constraint set, are all regular. And you have found all x star, lambda star, u star triplet that satisfies this condition. This condition, right? Then you are guaranteed to have every local extremizers in your what you have just found. So suppose you can evaluate them. And you compare the functional values. And you may be able to say that you have found some local or global optimal solution. Okay. But since this is not enough in many cases, and as far as you have second order continuous differentiability, you may rely on second order conditions. These are necessary conditions, so you can sort out some of the candidates. Hey, it seems that some of the triplets do not satisfy this condition. So definitely they are not local minimizers. Okay? Okay, minimize. Got it? So you may remove some of the candidates. Even though you have used first or second order, you are just guaranteed that they may be, right? They may be, right? The local minimizers. Okay? They may not be local minimizers in some case. So you further test with the second order sufficient condition. The problem is that sufficient conditions are not powerful every time. For example, suppose one of your, so by solving this one, you have this pool of triplets. Then you apply the second order condition, so you have smaller sets survive. Now you test every triplets with this condition, and it seems that everyone fails. But that does not say that there is no strict local, there is no local minimizer. It only says about strict local minimizers necessary condition. Got it? So be careful. We will see some examples. Now, let me a little bit twist and change the order. Okay. So let's see some examples. That would be better. So here goes high school type problem. I really love this one. So we want to minimize this second quadratic function actually. Subject to, what is this? This is the straight line, as you know, as you learned in high school. This is x1, x2 plane. And what is this one? This is the half space, so this area. Got it? So intersection of these two constraints is simple half line, right? So this is the feasible set. Now, here you want to minimize this one. If you were a high school student, probably, since you know this is this straight line, you replace x1 with x2 minus 1 here. And then this becomes a function only of x2, and you have the range of x1, right? Or range of x2. So it's what? It's just a minimization of a quadratic function on an interval. So this problem can be easily solved. Now, what we want to do is not just using our intuition and this graphical models, because our problems are much more complicated. It's not like this two-dimensional optimization problem. Okay? For example, if we have three-dimensional case, it's hard to figure out the constraint set and parameterize other variables to a single variable like this. Okay, so we need systematic way. So that's why we developed this theory. And this theory is very old and called Lagrange multiplier theorem and Lagrange multiplier technique. And the story is like this. First, I emphasized many times about regularity or some feasible x is regular. So let's consider the simplest case where we have a scalar equality constraint function. So where lowercase m equals 1. Got it? Because this is the simplest and easiest to understand. And also, we are going to visualize this situation with n equals 2. Got it? So with n equals 2, we can easily visualize our constraint set. Am I right? In the plane, in the two-dimensional plane. Now, so we have be careful. This is scalar, so I have written a scalar 0. Am I right? M is the number of equality constraint functions. Now, whenever we see continuously differentiable F0 or H, we are interested in local property. This means we are interested in local property. When we have first order continuous differentiability, and if we have local property, what do? We approximate involved functions by using Taylor series up to order 1. Got it? So the idea is like this. So here we need to remember that suppose we expand at let's say at x star. Okay, then what do we have? We have C1, F0. Since we can differentiate F0 once, we differentiate. So here we have the gradient evaluated at x star. And what? Transpose x minus x star. Now can we differentiate once more? No, we assumed F0 is in C1. Just continuously differentiable one time. So here goes our little o. You may hate this, but you can, anyway, we are going to ignore it. And 1. Okay, got it? Since f0 is C1, we have up to first order and little o of 1. Got it? So, we can approximate this function like this for x in omega and x in omega, the constraint set, right? Because the constraint set is an intersection of implicit and explicit constraint sets, where implicit constraint set is what is contained in the domain of this function. So we can do this. Got it? Now we do the same thing for the equality constraint function. So check whether your expectation is correct. So let me do this. Domain of f0. Domain of h. Got it? By the way, why don't we have h of x star? Why? Why don't we have h of x star? No, we assume that x star is feasible, which means that h of x star is 0. Got it? So this is 0. Now let's see first the constraint set, first order approximated. Got it? So what we want to do is that we want to set this function equals 0 around x star. So h of x equals 0 is almost same as what? Gradient of h, x, of course, around at around x star, okay, is this one. Am I right? Because this is the approximation of h near x star. Yeah. See that? hx equals 0 is the constraint set. Now we want to kind of approximate this constraint set near x star. So instead of equating this equals 0, let's equating this equals 0. Right? Around x star, they must be almost the same set. Am I right? Almost. So now here the idea is like this. In 2 dimensions, suppose this straight line is h of x equals 0. Why not straight line, this closed curve, why I write this way? For example, consider a 2-dimensional function that has shape like that. And this is your level 0. What will happen? You may have such a constraint set. Right? This is a level set of h with level 0. Right? Now, suppose this point is x star. So x star is what? Feasible. Am I right? Now, around x star, what do we do? instead of using this curve, we are going to use this straight line to approximate our constraint set. That is the idea. Got it? And then we want to analyze what happens. Now, so we need to examine that one. Okay? So this is approximate omega near x star. And what is the objective function near x star? We've seen that this is the approximation. Am I right? The first order approximation of the objective function. Right? Now, we assume that x star is a local extremizer. What does that mean? Local extremizer. What does that mean? Near x star in the constraint set, when we move following the first order not just first order. If we move around x star, okay, very near x star, what happens? Extremizer means that function value does not change. As you remember, like this. And you may not understand this one, so let's recall your old friends, the one-dimensional functions. Suppose you have a function like this, okay, in one-dimensional case. What are the local extremizers? How did we define in unconstrained optimization problem? For example, here, this point, I claim this is a local extremizer. Why? If you move around here, the functional value does not change much. Okay? Much is kind of vague, but since the function is differentiable, and its derivative here is 0. This satisfies the definition of local extremizer. I also claim that here, this is local extremizer because the slope is 0. And same. Got it? So, this is true. Okay? Local extremizer means that the objective function value does not change much, or you can say it does not change locally, okay? When you take that h goes to 0 in your limit process, okay? So now let's compare these two and see when do we have this function almost same as this one. What does that mean? This is, see this, f0x does not change much near x star. At x star, the function value is this one. What does that mean? If you change near x star inside the constraint set, approximated as a straight line here, this part will be 0, right? If x star is a local extremizer, this one must be 0. Am I right? On this straight line. Got it? Now, when do we have? So it's like this. See that? This one looks like this. You have a, sorry. This is something like this. This is a vector, right? Column vector. So, for example, you have ax plus by equals c. Or let me see. No, let's do this. ax1 plus bx2 equals c. So this one looks like this. Am I right? In two-dimensional case. See that? Here you have x1 minus x1 star and x2 minus x2 star. And what is this one? This is a 1 by 2, this trend, 1 by 2 constant. Am I right? So if you inner product these two, you have such straight line in two-dimensional case. Am I right? Like this. When this is not a straight line, when this is not a straight line, when this vector is 0. Am I right? When this vector is 0, this is not a straight line. But when this is not a 0 vector, this is a straight line. Passing through x star. Am I right? You've learned this in high school math, right? This is an equation of a straight line. So confusing. So what is this set? This is a graph if you draw this one. Okay? This is a set of points, x1, x2. And we call this a straight line. Am I right? So in two-dimensional case, it looks like this. Now x minus x star is what? What does this mean? It's orthogonal to the gradient of h. Am I right? So here, this vector is nothing but the normal vector to this straight line. Am I right? So this is the normal vector to this straight line. Now, we can move around this line that is orthogonal to the normal vector. Now, what if you move little bit, your function increases or decreases? Then x star is not a local extremizer. Am I right? Now, see this. You have a scalar valued function. What does this mean? This is a gradient vector. If you move along this direction, objective function value increases. Suppose your gradient of f0 looks like this. What will happen? If you move this direction, the function increases, and that direction, function decreases. Then when x star is local extremizer with non-zero h, gradient vector must be parallel to the normal vector of the straight line. In the case, if you move that direction or that direction, function value does not change. Got it? So this in the case with m equals 1, what can you say? Suppose x star is a local extremizer, and fortunately this is not a zero vector. Then we always have a straight line. It may be perpendicular or it may be parallel, but if it is not zero, it is always a straight line. In that case, if gradient of f0 is parallel to the normal vector, then this, x is a local extremizer, then what? They must be parallel. What does that mean? Some constant times the gradient of the objective function value is proportional to the gradient of that single equality constraint function. Or you may say that let me use some new. Like this. Am I right? So what can we say? If x star is a local extremizer and it's regular, which means that this is not zero, so there exists a straight line that well approximates our constraint set around x star, then what? There must exist some new star with which value the gradient is proportional to this. By the way, what if the gradient of f0 is 0? Then actually that is the condition for what? Unconstrained FONC, first or necessary condition. In that case, this is simply 0, right? So it includes when the gradient of f0 is 0. But it does not include the case with gradient of h is 0. Got it? That's why we have regularity. By the way, regularity in single equality constraint function is that this is non-zero. Got it? So let's go back and see. So here we have just studied this theorem when there is only one equality constraint function. And here we have what? Gradient of h x star times nu star is 0 when it is added with the gradient. Got it? Anyway, you know the form of this one from the KKT conditions. Differentiation of the Lagrangian with respect to x. So you already know. Now you know what does that mean when x star is regular. Okay? What does that mean? Gradient is proportional to the normal vector of the straight line in two-dimensional case, straight line that well approximates our constraint near x star. Got it? So this is the way to understand the special case of KKT conditions. And this condition is called the Lagrange conditions or Lagrangian conditions. So here goes the summary. The Lagrange conditions is like this. So x star satisfies the Lagrange conditions. Means what? First, h of x star is 0. Second, there exists some new star, it could be 0, that satisfies this condition. So these two lines are called Lagrange conditions. Sometimes these two conditions are written in a simpler form. So it's like this. You may say that, what? I understand. I also very confused when my professor stated the Lagrange conditions in this way. Now here, this gradient is not only for with respect to x, but also for nu. So what does that mean? By the way, what is this one? You remember Lx nu is f0x plus nu h of x. So the partial derivative with respect to nu is nothing but what? H of x. And that is 0. So you have, got it? So this is the second one, this is the first one. So it's confusing, but they are the same. Got it? So we have two conditions, but they are compactly written as this one. We differentiate the Lagrangian with respect to every variable and evaluate at x star and nu star and set it to 0 vector. Then we have first the gradient obtained with respect to x and the partial derivative with respect to nu, and if you set to 0, actually you have these two conditions back. Got it? So sometimes they just say that, okay, this is the Lagrangian, and by differentiating it and setting to 0, we have the Lagrange conditions. Got it? Now, let's generalize this to n greater than or equal to 1. So far, we consider the single equality constraint function. Now we are going to generalize. Before doing that, let me little bit defer this discussion. Okay. So let's see this approximations, first order approximations in depth. So it's like this. Consider the case where you have n-dimensional problem. Okay, so x is an n-dimensional vector, but still you have m equals 1. Okay, now you approximate h near at some x0 that is feasible. Then you have, as I just have written, something like this. Am I right? Now you set this equals 0. Now, what is this one? This is in general, a hyperplane. Okay. By the way, in two-dimensional case, so n equals 2, what do we have? Something like this, right? So straight line is a hyperplane. In three-dimensional case, what do we have? Let's say that this is a simplex. This is a triangle. Now let's expand that one for infinity. Okay? This is a hyperplane. So it's a plane, right? As we say in three-dimensional case. Now in four-dimensional case, four-dimensional, five-dimensional, we generalize this one. And they all look like this one. Got it? They all look like this. So you may say that this is the general form, and you see they have the same form. You expand this gradient H transpose X and minus gradient H transpose X star, and you move the second term to the right side, then you have this one. Got it? So this is the first order approximated our constraint set when m equals 1. Got it? So when m equals 1. Now, let's see what is the dimension of these first order approximations. What is the dimension? By the way, dimension is quite, how to say it? In many Koreans say dimension, but actually it's dimension, okay? Never say dimension, I will kick you out, okay? Dimension. And what does that mean by dimension? It's complicated, right? In linear algebra, it's very simple. But if it is not, well, what does that mean? Sometimes you can interchange or dimension with a degree of freedom. Not always, but this is much easier to understand. You have some freedom. And how many freedom do you have? Now, if you can only live on this straight line, how many freedom do you have? Say, suppose this is 0. Then every point can be parameterized by a single parameter. Distance from this point. Am I right? So this straight line has degree of freedom or dimension 1. Am I right? Of course, at some x star, the gradient may be 0. In the case, it's not a straight line. So in order to claim this one, I may have to say that the, every x in omega is regular. Special case. Okay? In special case, first order approximation has dimension 1. What about this one? You have plane, two-dimensional plane. Am I right? So in this case, 2. Now, for the four-dimensional space, your hyperplane will have dimension 3. Am I right? So, in general, in n-dimensional case, you have dimension n minus 1. When what? When m equals 1. So what can you guess? This one looks like this m. Am I right? This minus 1 may be from this one. Actually, that is correct. And let's see. Where is 7? Okay. Now consider the case where m equals 2. Okay. So let's do it one by one. And 6, 7. Okay. So m equals 2. Now, let me see. So x is still in n-dimensional case, and we have h1 of x, h2 of x. Am I right? This equals 0. That is the constraint set. So now we approximate each constraint function using first order approximation at a feasible x star. Then we have gradient of h1 x star transpose x minus x star. h2 of x approximately equal to gradient of h2 evaluated x star times x minus x star. Now we set this equals 0, set this equals 0. So at around x equals x star, our constraint set is what? Must satisfy this condition and that condition. Now let's see in two-dimensional case. So in two-dimensional case, so value of n So we have x1, x2. And now, what can we say? There are two cases, actually. Actually, there are three cases. Okay. When one of the gradient vectors is 0. Okay, let's forget about that. Okay. No. All of what I say. One of the gradient vectors is 0. In that case, we go back to the previous one. Now, second case is that this vector is proportional to that vector. Then they are the same. So let's forget about that cases. So let's assume that gradient of h1 x star and gradient of h2 x star, this matrix is of full length. Okay. To say this, we assume that m is less than or equal to n. Got it? In that case, we may have something like that. This is our omega. Am I right? Around at x star. Got it? Omega may be different, but around omega x star, we have this single point. Because the constraint set is the intersection of two straight lines. Now, what is the dimension of the omega x star? This point requires no variable to specify. So dimension is 0. Now in three-dimensional case, we also assume that the normal vectors of two hyperplanes are not proportional. They are none of them is 0. Then what happens? We have two planes intersecting. Then what do we have? We have a straight line. Am I right? That straight line has one dimension. So in four-dimensional case, you may have 2, and general n-dimensional case, you have n minus 2. Am I right? Under what? Under this condition. Actually, this is the condition for regularity. Okay. We call this condition regular. Now let's go back to our m equals 1 case. You have a single vector. Single vector is full length. What does that mean? It is not 0. So it's the same as what we defined here. Okay. So here we assume that it's not 0. Got it? So they are the same. This is the regularity. And this is the two-dimensional case. And you can generalize for general case. Then you have this. Okay? Got it? Now, let me just state it the general. Yeah, general case. So let me go back. Yeah, general Lagrange theorem. So what is the general Lagrange theorem? The claim is this. So as you've seen already, H star is feasible, and the gradient of the objective function is what? Is a linear combination of gradients of the equality constraint functions at x star. Why this is so? Okay. You have to remember why this is true. We have actually what? The intersection of gradient of hi x star x minus x star. I from 1 to m. When and also we assume regularity. So we assume that these are linearly independent vectors. Got it? Unit transpose. Okay. Now the idea is the same. Okay. You can move only to the direction that is what? That is orthogonal to each one. Right? You can move only to the orthogonal direction. So this is same as x minus x star is a member of what? Null space of what? Gradient h1 star, gradient h2 star, gradient h m x star. Am I correct? No, I'm not correct. Okay. Null space of this matrix h1 of x star transpose, gradient of h1 x star transpose, gradient of hm x star transpose. Right? So null space of a matrix means that what? You multiply some vector z and you have 0, right? So as you see here, you multiply x minus x star here, and you have 0. Oh, okay, something's missing here. Scalar. Got it? So x minus x star is in the null space of this one. And what must happen? As you remember, f0 is from the approximation of the objective function around x star. Now what do we want? When we move in this space, this value must be close to 0. Am I right? Then when can we do that? When this is spanned by that one. Right? As you know. Okay? So any member in this null space is orthogonal to this one. What does that mean? This must be spanned by these vectors. That's why we have that one. Okay? Got it? So it's a linear algebra result. So we may say that the linear combination of gradients must be the gradient of f0. Okay. It's same as the special case with m equals 1. Okay, as you've seen here. Okay, so that is the theory of the first necessary condition. They talk about a lot of tangent plane and tangent space, but I believe this is a better explanation. So we expand the objective function using first order approximation. We expand the equality constraint functions using first order approximations. And then we use linear algebra result. then we don't need to define tangent space, tangent plane, normal space, something like that. Anyway, so let's see an example. Here is a quadratic objective function, and here is a quadratic constraint. So suppose we want to minimize this one, subject to h equals 0. What kind of problem is this? What is the name of such problem? Quadratically constrained quadratic problem. Simply QCQP. Okay? This is simple QCQP problem. And they are sometimes easy to solve. You will see. Now, how can you solve? If you are a high school student, you will draw a figure. So first, you will draw the constraint set. What is that? That is an ellipse, right? And now this is a what? The level set of f of x is circle. So actually, this problem can be graphically solved like that. So this is ellipse is the constraint set. And now this is the level set of the objective function with objective function value 1/2. And this is the level set of the objective function with level 1. Got it? And now this example shows that if you find every x vector and new x star and new star that satisfies the Lagrange conditions, you find these 4 points. This one, that one, this one, and that one. Okay, you can find that. For example, so here, gradient is this one, and gradient of h is that one. Now, one good news is that, as you see here, x1 and x2 cannot be 0 at the same time. Am I right? If both are 0, it violates the constraint. So what does that mean? Every feasible x1, x2 is regular, because this vector is not 0. This is a great news. Every feasible point is regular. So we just need to find the x and new pair that satisfies the Lagrange conditions. And then every local extremizers will be included. Am I right? So you solve this one. It's not that difficult. If you just set the full differentiation of the Lagrangian function is 0, then you have 3 equalities. Actually, third one is what? Just the constraint, right? Primary feasibility. And now you cancel lambda and blah, blah, blah. You have 4 points. And these 4 points are what? These 4 points. We just found our high school approach. Got it? So this problem can be solved using our high school optimization technique. And also we can rely on Lagrange multiplier theorem. Now, let's check the objective function value. At x1 and x2, we have 1/2 because the level set was 1/2, level was 1/2 and 1. So what can we say? Maybe these are local maximizers, and these are maybe local minimizers. Or we may have very strange function. But actually, what do we have? Probably you remember Weierstrass theorem. What is a Weierstrass theorem? If you have a continuous function defined on a compact set, in Euclidean space, compact if and only if what? Closed and bounded. And this equals 0 is closed and bounded actually. So what does that mean? This problem have what? Minimizer and maximizer. Always. And minimizer and maximizer, which means global minimizer and global maximizer, must be what? When they are differentiable, they must be local maximizers and minimizers. And every point is regular, so they must be these x1, x2, x3, x4 must be minimizers or maximizers. Can it be maximizers? No, because this has larger value. So you can conclude, so you can combine the Weierstrass theorem and Lagrange multiplier theorem to conclude that these are local, actually global, in this case, minimizers, and these are global maximizers, given this QCQP problem. Now let's see some more examples, and this is interesting. Now the problem is very simple. Suppose you have, you can utilize unit area paper, and you want to make a box. Okay, let me say this. You are allowed to make a box with the surface area is 1. What is the shape of the box that maximizes its volume? Got it? So let's say that with height and depth as x1, x2, x3. Then this is the volume of the box. Am I right? And the summation of these three products are what? Of course, times 2 is the surface area. So let's say that surface area is 2. Got it? Now, we want to solve this problem. How can we solve? And you may say that, wait a minute, one constraint is missing. What constraint? x1, x2, x3 must be positive. But it's missing. Is it okay? You must be careful. Okay? We can relax our constraint anytime if it helps us to solve the problem. Got it? For example, you want to find some optimal point in a constraint set. But constraint set has very weird shape. So you relax a little bit and, for example, find that your constraint set can be functionally described. What does that mean? By properly defining an equality constraint function and inequality constraint function, you can little bit relax your constraint. That's good, actually. Now you solve the problem, and at the final stage, you remove those unfeasible ones. Okay? So here, we relax by removing the positivity condition on x1 and x2, x3. Of course, you can put x1 greater than 0, x2 greater than 0, x3 greater than 0, and then use the KKT theorem we are going to study in chapter 21. But by relaxing this one, by removing the inequality constraints, you can use Lagrange multiplier theorem. So let's do that. Got it? So that's the idea. Relaxation is one of the most powerful techniques in optimization. Sometimes by relaxing, you can find the global optimal solution very easily. But with all the constraints, sometimes you never solve. I have experienced myself in solving some optimization problems. Anyway, so here, these are Lagrange conditions, and as you see, the fourth one is nothing but the primary feasibility. Then you can solve this one, and it seems, as you see here, what does this mean? This equals 0 means that x1, x2, x3 are all 0. But that is not feasible. So good news is that every feasible point is regular. So we can use the Lagrange multiplier theorem to find out every candidate local extremizers. Got it? So we find, and sometimes we must use our intuition. Okay. So here what we do is that we use a symmetry. Okay. If x1, x2, x3 is optimal, x2, x3, x1 must be optimal, something like that. So we use symmetry and end up with only one candidate. What does that mean? This must be the optimal solution. Got it? Even though we relax the constraint, we can find only one solution. And that is feasible. What does that mean? That is our optimal solution. Okay, anyway, here comes another one. with two equality constraint functions. And as you see, the gradient of the first function is here, okay, as a row vector. And gradient of the second function is here as a row vector. And you see, these two row vectors are linearly independent. What does that mean? Every feasible x is what? Regular. Good news. Okay? Two rows are regular. Okay? These are simple transposition of the gradients, right? So every point is regular, and the dimension is 1 because this is rank. The rank is 2. Okay? And we find. Okay. There is no solution here. Okay. Let me see. Okay. This isn't just an example. By the way, let's see this figure. Suppose that this is our constraint set omega. In this node, it is denoted by S. So this is the constraint set, okay, in this case. Okay. And as I told you, this is a constraint set, but for example, at x star, what we do is that we do first order approximation. Then what is that? That is a straight line, tangent line. Okay. Now consider in a higher dimensional case. What do we have? When m equals 1, we have a hyperplane as our approximation of the objective function. So they define tangent space, but you already know why these definitions are there. They talk about what? They talk about this first order approximation near x star. Got it? So my explanation may be more appealing to you. And in three-dimensional case, say that this is the surface of the constraint set with single constraint function. Now what do we have? We have a tangent plane at x star. Am I right? When m is more than 1, then you have intersections of them. So I will not talk about normal spaces, and you already know. Okay. So here goes an example with two equality constraint functions. So you differentiate it again, you see that every feasible x is what? Regular. Good news. And you find, by solving these Lagrange conditions, you find candidates, 3 candidates, x1, x2, and x3. Now let's see the quadratic programming problem like this. Of course, there could be some inequality condition for general quadratic programming problem, but here we only have this affine constraint. And such problem can be solved easily in some cases. For example, when Q is invertible and positive definite. So what does that mean? This is a quadratic form, right? Without that one, what is the optimal solution? X is 0, right? But now we have a linear affine constraint, so we may have no idea what's the solution. But this has what? This has a closed form solution. That's why this is important. And now we are going to use Lagrange conditions to find the optimal solution. So we form the Lagrangian and differentiate to get the 2 Lagrange conditions. But one is just the primary feasibility. And now we cancel lambda or x to have, in this case, we replace x with lambda. And we have lambda is written in terms of the system, the problem parameters. And then we plug this in here, get x star. And since Q is positive definite, and here we assume A is of full length and M is less than N, every X feasible is regular. And we have single candidate. What does that mean? This must be the solution. Got it? So we are very lucky in this case, and this is the solution. There is an optimal control example, but you read it. I'm not going to cover this. This is called the linear quadratic regulator problem. And just remember this one. That may be enough. You may see sometime LQR problem. in your lifetime. So we are done with the first order conditions. Second order conditions are more difficult, and there is no derivation in our lecture note, but you can find the derivations. And what I want to emphasize is that remembering the second order condition is very easy. The second order necessary condition is almost same as the first order necessary condition up to here. So x is a local, not now minimizer because we use second order. Okay, so extremizer becomes minimizer, and still we assume regularity because we claim that there exists new star satisfying together with x star the FONC. So this condition. And what is this one? Hessian matrix of the Lagrangian function evaluated at x star nu star. And now this is this quadratic form. So actually what we do is this. We do quadratic approximation. Okay? We do second order approximation to the objective function and the constraint functions. Okay? So that's it. So the idea behind this second order necessary condition is that instead of doing only the first order approximation, we do second order approximations for the objective function and the constraint set. Okay. So we have a what? Quadratic function, not the straight line, but a parabola type approximation. And in order to have that one, we need a little bit lengthy derivation where we need to utilize this condition. Then after plugging in, we have this nice property, but here y, actually this y is nothing but x minus x star actually, as you expect. Because when we approximate the function so second order approximation. Second order approximation is this one, around that x star. You have the same first order term, and you have the quadratic form. Because here originally you have something like that. Got it? So here x minus x star is just replaced by y. Got it? X minus x star is replaced by y, and combined with the approximation like this one. Okay, got it? So you utilize the first order and the second order approximations to have the second order necessary condition. So here, x is in the, y is in the tangent space, subspace, means that actually here, you can say that x minus x star transpose, x minus x star transpose, this is x minus x star, then what does that mean? X equals tangent space of x star plus x star. Got it? So we have the same thing. We have linear subspace, and on that subspace, this is positive semi-definite. Okay. I'm not going to derive everything. Okay. It seems that I'm too over time, but anyway. And this is actually quite different. Okay? Here we have one more condition, strict local minimize, strict. And here we remove equality. And also we put the condition that y is not equal to 0. Means that x is not equal to x star. And we have the same tangent space x minus star. Okay? So this is the kind of null space to the matrix consisting of gradient vectors of H. Anyway, so I will stop here for chapter 20, and we'll continue next time on chapter 21. That's all for the day.